In this class, we are going to discuss about some more examples. Let's consider the first example. Here, we have to find out the load resistance for which maximum power can be transferred in this network. Now, state and prove the maximum power transfer theorem. Calculate Thevenin equivalent resistance across terminal A and B and the maximum power of the load resistance RL. Here RL is unknown and that's what we have to calculate. For maximum power transfer theorem, by the definition, we know for a load the maximum power can be transferred when load resistance becomes equal to Thevenin equivalent resistance of the rest of the network. Now considering the first part, let we are considering a network having VTH and RTH, RL. Here it is RL, this is RTH. In this network, the power across the load can be find out as maximum by knowing the current. I is equal to VTH upon RTH plus RL. Now this is the current. The power in this circuit is, or if you want to find out across RL, PL is equal to I square RL. I we are knowing VTH upon RTH plus RL whole square into my RL. In this equation, now in order to find out the maximum power, the variable component is RL. If we derivate this function with respect to RL and putting its first derivation equals to 0 and then finding out the condition, it will gives RL is equal to RTH. And that's what the condition for maximum power transfer theorem is. Now we have to find out the maximum power in this circuit. Before calculating the maximum power, we must know what is the value of this load resistance is. This load resistance, to find out load resistance, first of all we have to find out Thevenin equivalent resistance of the network. Now in this particular network, the Thevenin equivalent resistance is calculated when all the all the sources are replaced with their internal resistance, because the current source having internal resistance as infinity and hence it is open circuited, and the rest of the network can be redrawn over here. This is looks like that when all the sources are replaced with their internal resistance. Now from here we can find, looking from here, this is the resistance RTH across terminal A and B. This is 2 ohm, this is 4 ohm, this is 1, this is 3. As this path is open and hence there is no contribution of 2 ohm resistance, and hence we can say 4 and 1 is in series with each other and the combination is in parallel with 3 ohm resistance. Then it will be the RTH. Here it is 3, 1 and 4. This is 5 and this is 3, and hence the parallel combination will give RTH. RTH will be equals to 3 in parallel with 5, which is equals to 3 into 5 divided by 3 plus 5 is equal to 15 divided by 8 is equal to 1.875 ohm. Now we are VTH. To find out the VTH of this circuit, when in order to find out VTH of this circuit, we are knowing that in order to find out VTH, let me consider this network again. There is a resistance, there is a source, this is 1 ohm, this is 3 ohm. To find out VTH, that is AB, this is equals to nothing but VTH. This is 3 ohm, this is 1 ohm, this is 4 ohm, this is 2 ohm, the current is 4 ampere. Now here VTH is VTH depends upon this path. This is these two resistance are in series, and this series combination is in parallel with 4 ohm resistance. Then this network can be redrawn as this one. This is 4, this is 4, this is 2. Now the parallel combination of these two is nothing but 2 ohm resistance. It will be 2 ohm. This is 2 ohm. Now total current supplied by the source is 4 ampere, and this current is divided equally in these two branches, and hence here current will be 2 ampere. Now the we have to find out voltage across this 3 ohm resistance, that is nothing but the VTH, which is given by VTH is equal to 3 into 2, that is equal to 6 volt. Now we are knowing the VTH, we are knowing the RTH, then we can calculate P max. P max will be equals to VTH square upon RTH 4 times of RTH, which is equals to 4.8 watt in this case. Now considering the second problem, in this case we have to find out the current through 6 ohm resistance by using superposition theorem. Now considering the first source, 9 volt source, first according to superposition theorem we have to consider one source at one time. Let here we consider first source as voltage source, and the other sources are replaced with their internal resistance. Here we are having a current source, and this current source is replaced with the internal resistance, and the internal resistance of current source is infinity. Now this will be the equivalent network. Now this network can further reduce, these two are in parallel, and the parallel combination can be reduced to this one. Here we will be having only one resistance, that resistance is 3 ohm. Here it is 3 ohm resistance. We are having one resistance over here. The parallel combination of these two is, the parallel combination of 3 and 6 is 3 into 6 divided by 3 plus 6, which is equals to 2 ohm. Now this is 2 ohm, this is 3 ohm, these are 3 ohm. At the voltage here it is plus minus. Now this voltage 9 volt appear across these two elements also, because now they are in parallel, and hence we can find out current in this path. Let's consider this current is I. This I is equal to 9 divided by 5, 3 plus 2, that is equals to 4 point, this is equals to 9 divided by 5 will be equals to 1.8. This is 1.8 ampere. This current is flowing in this parallel combination of this branch, and hence the current through 6 ohm resistance, let's consider it is I dash, and I dash due to one source is 1.8 is the total. Applying the current division rule, that is total current divided by resistance of opposite branch divided by total current multiply resistance of opposite branch divided by sum of resistance, which is equals to 0.6 ampere. Now this is the current due to 9 volt source. Now considering the second source, in case of second source we are replacing the voltage source with their internal resistance, and this internal resistance of voltage source is 0, and hence the circuit will become short circuited. Now we are having a resistance of 3 ohm, and current source of 3 ampere is connected in the rest of the circuit, which is having this combination. This is 3 ohm because this path is shorted, and hence this path is also considered as shorted. This is 3 ohm, this is 6 ohm, and hence the resultant network will be reduced to this one. Now from here we can see all these branches are in parallel, because we can redraw this network as this is parallel combination is nothing but 2 ohm, and this 2 ohm resistance is in parallel with the current source. This is 2 ohm, this is 3 ohm, the source is 3 ampere source. Now these two branches are in parallel, and hence here also we can apply current division rule. Now on applying this current division rule, then we can find out I in this branch. Over here the total current supplied by the source is 3 ampere. This is 3 ohm. The opposite branch, the parallel combination is having 2 ohm, and hence the current, total current is 3, total current into my resistance of opposite branch is 3 ohm, into my 3 divided by sum of resistance 3 plus 2, that is equals to 9 by 5, which is equals to 1.8 ampere. Now this current is flowing in the parallel combination of 3 and 6. Now again applying current division rule, then we can find out current through 6 ohm resistance. Then I double dash. Let's consider this current is I double dash, which is equals to total current 1.8 into my resistance of opposite branch divided by sum of resistance 3 plus 6 is equal to, that is again 0.6 ampere. The current due to first source it was 0.6. The current in 6 ohm resistance due to second source it is 1.6 ohm, 0.6 ampere, and hence the resultant current is 0.6 plus 0.6 is equal to 1.2 ampere. Now this is the current. We are, in order to find out VL will be equals to I into my R, and I is 1.2, R is 6, which is equal to 7.2 volt. Answer. Now considering the another example, in this case we have to find out the current through and voltage across RL using mesh analysis. Now according to mesh analysis, let me consider that there are two loops I1 and I2. In case of in first loop, let's consider loop 1. Here it is plus, it will be minus, it will be plus, it will be minus. The polarity is defined according to this one. This will be plus, this will be minus, and the rest of the polarity are defined. Now considering the first loop, we are moving from higher potential to lower potential. This is 8 I1, then lower potential to higher potential. This is plus 8, higher potential to lower potential, minus 4 I1 minus I2, and then lower potential to higher potential plus 5 is equal to 0. This is the KVL equation for first loop. On simplifying this equation, it will be minus 12 I1 plus 4 I2 is equal to minus 13. Let's consider this equation is first. Now for loop 2, in loop 2 apply KVL, and this is minus of 10 I2, then minus of, we are moving from higher to lower, then it will be 10, then we are moving from lower to higher, then it will be plus 4 I1 minus I2, then higher to lower again minus 8 is equal to 0. And on simplifying this equation, we will get 4 I1 minus 14 I2 is equal to 18. This is equation second. From equation first, and second we can find out I2 is equal to minus 1.079 ampere. Now knowing the I2 we can find out VL is equal to the total resistance is 10 ohm into minus of 1.079 which is equals to minus of 10.79 volt. This is answer. This is the current through 10 ohm resistance which is nothing but I2 and it can also be written as IL, whereas VL is nothing but the voltage across resistance, that is VL is equal to this one. Now considering the another example, in this case we have to find out the current through 5 ohm resistance. Let's redraw this network. This network can be drawn as like that. These two network are same. This is 5 ohm, this is 10 ohm, this is 10 ohm, this is 10 I1, and I1 is the current flowing through this element. This is I1, 5 volt plus minus. Now in this case we have to find out current in 5 ohm resistance, and there is no rule to apply whether nodal analysis or mesh analysis. To solve this type of network, so first of all identify the number of nodes. Here it is one node and this can be taken as a reference, and hence there are two nodes only and it is easy to solve using nodal analysis. Now at this node, let we consider current in this branch is I2, and here current is defined as well as current is defined in this branch also. Now at node A, we can say applying KCL at node A, applying KCL, that is equals to I1 plus 10 of I1 is equal to I2. Here I1 is equal to 5 minus VA upon 10, and I2 is equal to VA minus 0 upon 10, and in third branch this 10 I1 is already defined. Now putting this value over here in this equation, that consider this is equation first. In this equation if we put these values, then it will be given as 5 minus VA upon 10 plus 10 I1 is equal to VA by 10. In this equation we know the value of I1 also, 5 minus VA upon 10 plus 10 into 5 minus VA upon 10 is equal to VA upon 10. Now on simplifying this equation we will get 5 minus VA plus 50 minus 10 VA is equal to VA. From here 12 VA is equal to 55, that is VA is equal to 55 divided by 12, which is equals to 4.583 volt. Now in this circuit, this is the voltage VA. Putting the value of VA in this equation, we can find out I1, and putting the value of I1 in this circuit here, we can find out current flowing through 5 ohm resistance, and therefore current in 5 ohm is given by 10 I1, which is equals to 10 into I1 is 5 minus VA, 5 minus VA. VA is 4.583 divided by 10, and this is equals to 0.417 ampere. That is answer.